for the introduction. So yeah, today I'll try to be a bit broad, so I won't go into too many details. So if that's a funny one. So if anyone has any questions, feel free to ask. So I'll also try to introduce a few of the other things that I do, because I'm new to Munich, as was mentioned. So maybe in the interest of starting some collaborations, I'll try to inject some of the other ideas that I work on. But the main point that I want to talk about today is a bit different, and it's quantum control with matrix product states. So the plan, I really don't know why the blue is doing that, but what can you do? The plan is I'll try to spend most of my time on the motivation. Hopefully everyone will then understand why this is even an interesting thing to look at. And then I'll give you a bit of an overview of what has been done before, and then introduce two of our results on this matter. So what do I generally care about when I talk about quantum many-body systems? The things that I'm typically interested in, and hopefully some of you were already convinced yesterday by some of the talks that this is interesting, is out-of-equilibrium properties. So for instance, you can consider, right, maybe I have some sort of quantum system, and I heat it a little bit on one side, and I might ask, okay, now, how is this energy that I've added here, how is this transporting through the system? Or indeed at long times, does this then thermalize, or is there some reason, some mechanism behind that prevents thermalization? Or, similarly, good examples of this would be maybe these quantum many-body scars. Maybe you can look at localizations. So these would be states that you can start with for one reason or another, do not thermalize. Or they may show memory effects that last much longer than you would generally expect. So if I look at the first one, right, typically what we would do is, if I do theory, right, maybe if the model is integrable, I can solve it analytically, although this is not super, it's not entirely rigorous of a theory yet, but we believe it works. We can check things numerically, right? I can do exact normalization, I can do tensor networks, maybe some Krylov methods, right? So there's lots of things that one may try, but they all suffer from some limitations. On the other hand, right, if you're an experimentalist, right, you have various setups. So you have superconducting qubits, you can do cold atoms, NV centers, and you can try to probe the same questions. And as an example, right, maybe I take the Heisenberg model, which you've probably all encountered at some point. If I do this theoretically, right, maybe I'll end up using tensor networks in this case. So this is a plot from some slightly older paper. And I can extract the transport exponent, right? I'm not going to go into details of what it is. But the point is, if you do this experimentally, right, it turns out that you can get the same result, right? So the experiments are really coming to the point where the best thing that we can do with numerics or with analytical calculations, right, when possible, can actually already be probed, right? So such that I don't, leave this Google experiment up. Similar results were also done in Munich, right? So this is the same model, but now in continuous time. The previous one was obviously on a supposedly quantum computer, right? So it has to be discrete. And you can prepare these states, right? And then they let them evolve, and you can track how this thing is spreading. And from this, you can extract the same information, right? But really, the point that I want to get across is that this can now be done in experiments. And likewise, for the other thing that I mentioned, right? So for instance, quantum many-body scars. In fact, this is something that was first observed in an experiment, right? So this is from Lukin's group in Harvard, right? And what they do is they prepare their Rydberg atom array, and they use a special ramp to create a null state, right? So I just have up, full empty, or Rydberg state, ground state, Rydberg state, ground state, well, as close as you can get in an experiment. And you let this thing go, and you would very much expect this to just thermalize, right? So this should just quickly approach some sort of thermal equilibrium. Instead, what you observe are these oscillations, right? So we go from one null state, you go to the other one, you go back to the first one, and this oscillates on and on, much longer than it has any right to do. So this, of course, has since drawn a lot of attention on the theory side, right? So in theory, right, we'll take this terrible-looking Hamiltonian, right? There's some all-to-all interaction here, but gamma is usually 6 because this is van der Waals. So we'll say, okay, the first neighbor interaction is strong, right? The others are all 0. And we'll rewrite this as a PXP model. So here, P will just be a projector onto the down state, meaning that you're allowed to flip a state if and only if there is no neighbors that are already flipped or no neighbors that are in the Rydberg excited state, so whichever formalism you want to use. Right? But then there are some more recent results, right, which show that this null state that I mentioned here is not the only state that shows this behavior. So you can create a state that is very weakly entangled, right? I just add a little bit of entanglement because the previous one was obviously a product state. And I can find other states that show these revivals, right? So if I plot fidelity as a function of time, right, I see a revival every period, right? The period here is some strange number that's not relevant. And I won't go into the details of what these states are, right? But suffice it to say that you can find one, you can find another one, and you can keep finding them. So the question that I want to ask is, well, what is it, right, that we can observe in experiments, right? And I can show another example of something interesting that you can create numerically is you can create a state, which is this quantum many-body scar, which shows these oscillations, right, as we see in time. So here I just plot the probability that the state is in the excited state, right? So you see that I have a pattern, it repeats, but I put a perturbation here, and this perturbation spreads. And this really somehow relates, right, the two things, right? So I have scars, but at the same time, I can look at transport of energy, right? So if I plot energy, I'll see that this is almost perfectly conserved state, right? You can see, I hope you can see in the back, right, there's a bit of a correction, there's something flying out. So nothing is exact in this model, it's not integrable, I don't expect this to hold. But it's definitely much more stable than it has any right to be. So these are the things that we can see. But what else can we observe in an experiment, right? So can we see any of these other things? So there is a bit of a trick that was sort of used in the previous cases, right? So maybe I can just skip back, right? So this case, this is a state that they could prepare very easily, and then they let it evolve. And in this case, the Hamiltonian of the model is actually all that you want. So in general, however, if I want to see something in an experiment, I'll simplify this, as a theorist would. I only need three things, right? I need to be able to prepare the state that I want. So there is maybe a specific state, like I showed before, that you want to prepare, and that state will do something interesting in its evolution, and that's what you want to look at. So you need to be able to prepare that. Then you need to be able to do the time evolution, right? So whatever your experiment is, it needs to simulate the Hamiltonian that you're interested in. And then finally, you need to be able to measure something interesting, right? So in my case, I'll assume that these two are possible, right? And what I want to focus on is, well, how do I prepare a state? So how do I take a state that I can prepare, right? So I'll call this psi A. Let's say this is something that your experiment is able to do with a high fidelity. Maybe you do a destructive measurement and you can end up with this state. Maybe you have some protocol that enables you to prepare a specific state with a very high fidelity. I don't know. But there is a way to get some state, and you will know your system in this state. But what you actually want, for whatever it is that you want to observe, is a state, let's call it psi B, right? So assume this is some projection of my Hilbert space, right, so that I can draw it. I'm here, I want to get there. Now, how do I do this, right? I mean, I can go one way, I can go another way. In principle, I don't care which way I go, so long as I get the correct result. And this, of course, I mean, this has been studied to some extent. And maybe I'll just briefly go over the methods that are already known, right? So the simplest case is, okay, I mean, I can take my Hamiltonian, let's say, this is what's going to be doing the evolution in my state, and I can just write it as a sum of some operators and some prefactors. So the way you can think about it is, these BI, which are called B here because I was running out of letters, these are just whatever you can do to your system, right? So maybe you can shine a laser that acts as one operator. Maybe you can couple two together, right? That will then give you some interaction term here. So whatever it is you can do to your system, you put here, and then this just tells you, turn it on, turn it off, how strongly it should be on. You can do this, right? Then you can just say, okay, look, I have a cost function. The cost function is I take my state, I evolve it with whatever I've chosen this Ci of t to be, and I check for the fidelity with the target state, right? You can do this. People have done it. You can do gradient descent. You can do, chopped random basis approximations. You can do machine learning on this thing, and you'll get a result. But the issue is that this is a high-dimensional problem, right? You'll have some number of these operators, and each of these has a continuous function here. So yeah, you have to truncate this space. Is this a good choice of truncation? Whatever it is that you choose, you don't know. You'll end up with a result, but it's not great. So the question is, can I do something a little more analytical, right? Can I get a bit more intuition, and can I learn something on the way? So the second option, right, that you can go in somewhat this direction is, well, I can just use the adiabatic theorem, right? So I can find the Hamiltonian such that this psi A is always the ground state, and I'll set the ground state to always be at 0 energy for the sake of simplicity. So you can do that, and this will guarantee to you that so long as this Hamiltonian, which we will call the parent Hamiltonian for reasons that will become apparent later, so long as this Hamiltonian has a gap and you move infinitely slowly, you're guaranteed to reach the state that you're after, right? If you have a trajectory that connects state A to state B. This is all great, but what if you want to move a little faster, right? What if your coherence time is a little slower and you need to speed this up? Well, then there was a, well, almost decade-old result now, and the one that I will try to work on is called counter-diabatic driving, right? Basically what it says is, if I move at a finite velocity, then my effective Hamiltonian gets a correction from the rotation of the basis, right? So the question is, can I counteract this? So this is roughly what this schematics, this picture is supposed to show, right? If I move infinitely slowly, then I'm in regime A, right? The water is never tilting. If I'm moving, then I have a system force, right? It acts on the water, and maybe I'll spill some. But I can counteract this, right? I can add the second correction. So this would be this counter-diabatic gauge potential. And I can try to ensure that the system still stays in the ground state. Now, you can, of course, always do this. You can do this exactly if you want. But if you do this exactly, you have issues that the operator that you end up needing to add will be non-local. You will never be able to implement it. So what people have come up with is the following, right? You can say, OK, I won't go through the derivation, but you can come up with some operator G that looks roughly like this. And if I minimize G squared in some way, then this will give me the optimal correction that I can add in terms of this expansion with this B. So whatever operators that I can apply. So you minimize the trace square of the square. So sounds great. It's easy to compute, right? You just need to compute some commutators, right? But if this is local and if this is local, then this is really not that big of a problem. You can do it on your laptop in 5 minutes. But there's a bit of a problem when it comes to what it actually does, right? So like I said, right, this G, it's really parameterizing how you're being pushed out of whichever state you're in because you're doing this transformation at a finite velocity. So it's trying to minimize your leakage out of the ground state. That's good, right? That's what we want. But at the same time, it's trying to minimize any transitions at any excited state to any other excited state or even back to the ground state. That's bad, right? I don't care about these. I don't care about what happens here. All I care about is that my state, which is supposed to be here at the start, stays here. Anything can happen up there. And in fact, right, there's an exponential number of these, and there's only one ground state. So in general, you would expect that, OK, I mean, we're doing this optimization, but the likelihood that we're optimizing for the right thing is quite small. The better option would be if I were able to do this for the ground state directly, right? So I assume I have a ground state. Now I'm parameterizing with some parameter lambda. I compute G squared for this ground state, and then what that will do intuitively, right, would be just try to minimize transitions from the ground state to the excited states. So that's what I want, right? And this is where matrix product states now need to show up. So I'll assume that most of you are to some degree familiar with what this is, but I'll give a very, very brief overview. So the idea is that I will take my state that lives on some lattice, and I will encode it as a product of tensors, right? So if I draw this as a picture, it will look roughly like this. So there will be a tensor for each side. Here I just draw them to be the same. And in fact, for all of the derivations, we will simply assume this to be translation invariant, because that allows us to make proofs. But in principle, they can, of course, be different, right? So these legs on the sides, this is what you'll call the auxiliary dimension, right? So this is what you use to store information on correlations. And then the legs at the top, these are the physical dimensions, right? So your total physical space is simply the tensor product of all of these indices that are sticking out. So there are a few nice properties to this. One is you can always find the parent Hamiltonian, right? So if I don't think about it in the way you usually do when you think adiabatic, I can say, I don't care what the Hamiltonian is. I want to follow this line specifically for whatever reason. Well then, so long as this line is an MPS at every point, I can always find the Hamiltonian such that this is true, right? I can make sure that this is the unique ground state, that it's gapped, and I have everything that I need for the counter-diabatic approach. The second nice thing is, of course, that I can actually evaluate this, right? If this is an MPS, this is just a contraction of a local tensor. I mean, it is a little nasty, right? So this is a 2-point correlation function. I have to square it. I'll end up with a 4-point correlation function, but it's nothing that you cannot compute. So this is great, right? This means that I can just take the counter-adiabatic protocol, and I can just put MPS inside and say, well, look, if it's an MPS, then I can do this evolution. So let me show you an example, right? So let's do counter-adiabatic with an MPS, and for sake of simplicity, we already introduced the PXP model. So let me just take the PXP model, but let me say that if the X term, so if the flip term is acting on even sides or on odd sides, I will give it a different prefactor, right? So I have C1 and C2 here. This gives me one free parameter, right? I can change the ratio between them. If that's the case, and if I choose some random trajectory, that we won't discuss why it's chosen here, then I can see that indeed we perform better, right? So here I plot the minus log of fidelity over L. The reason for this is this quantity, as I take L to infinity, should go to a constant. But suffice it to say, lower is better, right? So the lower I am, the higher the fidelity. So if I just take the counter-adiabatic approach, right, I'll end up with this line, and see we end up somewhere here. Instead, if I take the counter-adiabatic approach, but I compute it only in the ground state, I immediately get an improvement. And this doesn't look like much, but this is the difference between this being stable for maybe 4 rounds and this being stable for maybe 50 periods, right? So it looks like a small difference, but that's the log tricking you. But those of you who are paying attention, right, you might notice there's a third line down here, which seems to be significantly better still, right? So if I follow this line, I can do this lap about 1,000 times before I lose fidelity. So what is that? So if I take this counter-adiabatic approach, right, and I just play with this expression a little bit, I can rewrite it in this way. Really, all I'm trying to minimize is the distance between the direction that I want to go at some point and the direction that I end up going, weighted by this parent Hamiltonian. Now, this is already a little strange, right? The reason for that is this parent Hamiltonian is not unique. So for any MPS state, there is an infinite number of parent Hamiltonians you can come up with. There's actually a nice way to construct them, which we'll touch upon later. And a very natural thing would be to just throw this away. I mean, why would I weigh the directions with anything, especially if this thing is arbitrary? So I can instead just say, okay, I mean, I'll throw that away, and then I'll do something that's called leakage minimization. This actually comes from the time-dependent variational principle, except now we're doing it in reverse, right? So those of you who are familiar with this, the idea is that you take quantum dynamics and you project them onto this classical manifold. Well, now we're doing the opposite. We have a direction on this manifold that we want to go to. We can simply project that up onto the nice linear vector space spanned by all of the operators B that we have chosen so far. So these are the things that you can do to your system. So if I do this, right, you can easily show that this just becomes a quadratic minimization problem, right? We can all solve this. I'll end up with something like this. And all I need to do to get this is compute a few correlation functions, right? So with MPS, that's really not a problem. But by doing this, we can actually get something that locally is geometrically optimal, in the sense that if I have this direction that I want to go to, and this is the direction I end up going to, if I take the difference between these two, that really is the closest you can get. And so what that means is that what I can guarantee you is not that at long times, this one has to be lower than the others, right? That I cannot show that. What I can guarantee you is that at short times, or at any point, this one has to leak the least. But you could still get, corrections, so the red could, for some reason, turn back down and go back into my system. Of course, the counter-adiabatic doesn't account for that either. That would be some sort of higher order, right? Because all of these, they look at it locally, and I just say, okay, at this point in time, where should I be going? Not what will happen later. Okay, so this we can do. It seems to work well. But now, what are the problems? Well, the problem is sort of twofold, right? It's like, how do I choose this trajectory, right? I said I can now drive along one specific line, but which one should I choose? Or conversely, well, if I choose a line, which operators should I be choosing, right? So maybe from an experimental point of view, it makes more sense to ask the opposite. It's like, okay, these are probably fixed. This is the thing that you can choose. And the reason that I say this is I can give you a very intuitive example. Like, let's say I give you a single spin on a block sphere, and I say, okay, rotate it around the x-axis. And then I say, but the operator that you have to use to do this is sigma z, right? So obviously, this is going to cause some problems. So it's this choice that we need to try and solve. And really the question that we want to answer is, can we guarantee that this thing will work well, right? I can guarantee it's optimal, but it can still be terrible. And to do this, we need to go to a slightly different approach. So for start, I need to simplify a little bit. I'll say, okay, now the operator can be anything that acts on at most r consecutive sides, right? All I want is locality. Theoretically, this makes sense. In terms of experiments, this, I think, is also a fairly reasonable approximation. Generally, the experiments are not very happy if we give them something that should be acting on 50 sides. But then, okay, now here I need to go into a few, this will be the most technical slide, I promise. A few details. Now I need my MPS to be injective. What this means is that for sufficiently large R, okay, I lost it down here, sorry. So for sufficiently large R, if I cut this MPS at some point, and I think of it as a map between two of these auxiliary spaces and whatever physical subspace it maps to, this map has to be injective. If this is true, then what I can do is I can build an operator called, let's just call it O, which is built from an inverse and whatever it is that I want at the top, right? So how should this work, right? If this is injective, I can build a pseudo-inverse, meaning that I can just sort of cut this, and then I can inject whatever I want on top. So for those of you who are familiar with biology, right, this is sort of like CRISPR gene editing, but you're doing it on an MPS. So I can do this, and then I just put this derivative term inside. In fact, I don't need to put it here. I can put it at any position, or I can split it in half. So long as the sum of these derivative terms is 1, I'll end up with the correct state. OK, so I can do this. So what are the properties of this O that I can build? Well, first, this is the exact generator of local dynamics, right? So this will do what I want exactly. There will be no error associated with it. Of course, I have to pay a price, right? Nothing is free. It's unfortunately not Hermitian. So, OK, looks like a problem, but the question is, maybe we can fix this, right? So we can try the silly thing, which is, OK, I mean, let's just make it Hermitian. I'll take this O, I'll add O dagger, now it's Hermitian, very good. Is this a terrible idea? Well, if I want to know if this is a terrible idea, what I need to do is I need to bound this error, right? So I know that OR to psi gives me exactly the derivative. That's what I want. I also know that O dagger R to psi is whatever I don't want. So this is exactly my leakage. So can I bound this? And we will skip all of the details. The answer is yes. In fact, I can bound it with an exponential. So the larger your R, I can show that we will get exponentially close to the correct state. We can test this, of course. I mean, there could be some mistake, right? So we can test it. If I just take the usual, I put this derivative in the middle, I'll get exactly the bound, right? So I scale exactly as lambda 2 squared. So our bound up to a constant seems to be tight. However, like I said, I can put the derivative anywhere, and this is what this alpha represents, right? So let's say I have alpha 1 derivative on first side, alpha 2 on the second side, and so on. All I need is I need this sum to be 1. There are no other restrictions. So if I optimize, if I just numerically play with it, I can actually get double the convergence rate. That's great. It means we can do better. It means our bound is not perfect. But it's much easier to bound the following. Right, and this also, because if you recall, right, the previous example where we did this with a variational optimization, this also means that that one has to be exponentially good if we allow for all local operators up to some range R. So in this way, we can show for both of them that there is a guarantee this will work, so long as you allow all local operators up to some range. OK, so I think I have about 30 seconds left. So what we show is, OK, I can do locally optimal quantum control if I use matrix product states. In fact, this is a bit of a lie. It doesn't have to be matrix product states. All I need is I need it to be a variational state such that I can take a derivative. And I need to be able to compute contractions, so expectation values, efficiently. So PEPs and other 2D things may be a problem. But it is definitely something that we can think about. Then we've constructed exact local generators, right? Okay, they become non-Hermitian, but by just making them Hermitian in the silliest possible way, you can show an exponential bound on the error. This means that, so long as we allow reasonably small but still local operators, we can actually get exponentially good results. But of course, many open questions remain, right? So I sort of swept this under the rug, but in this second construction, there are a lot of free parameters. And the question is, okay, I can build those operators, but can I make them quasi-local at least? Because we know that if I take infinite range, I can make a quasi-local generator. So how should I choose these free parameters for this to be true, and how can I choose them such that I can actually build that quasi-local step by step? This we don't know yet. Okay, like I mentioned, yeah, we can extend this to other variation manifolds, especially beyond 1D. And here specifically, there will be some interesting recent developments, right? You have neural quantum states which show good promise to do 2D, and likewise they can be used for something like this. You have isometric PEPs. So maybe there is hope to try and extend this to two-dimensional systems. And with that, I think I'm a bit over time. Sorry. Thanks.
Thank you very much, Marko. I think you actually did great on time. We started a little late, so that's very nice. I think we for sure have time for a question, if there is one in the audience. Anka is throwing.
Bro. Hey, so I'm pretty sure you've talked to Yorgos about this already, but I feel like the construction of the exact local generators is quite the same idea as approximating MPS with fixed points. So your OR is quite literally the renormalization fixed point of your injective MPS with a bunch of isometries on top.
Yeah.
So with that in mind, I don't get why, could you explain in more detail why this point, this local generator, what it has to do with the optimal quantum control, the counter-diabetic driving?
So no, so counter-diabetic driving is a separate thing, right? In that case, you have this parent Hamiltonian which weighs everything down. My point is that is not how you should do it. Okay? Instead, you should forget that parent Hamiltonian. And then the relation becomes, right, if I go, I have to go quite a while back. But if I go back right here where I decide what my Hamiltonian is, if I choose that this can be any local operator up to some range, then I can relate the two. Because then I can say, I can find an operator, which is this one plus its Hermitian conjugate, for which I can show a bound, right? So it will be an example, but it has to be included there, because that includes all of them. And if I can show a bound on this one, I can also show a bound on the other one, right? So, because that one is quadratic, and I can provably find the global minimum there. That's trivial. That would sort of be the correction. But indeed, right, if I take anything else here, right, if I remove just a single operator here, then I can no longer prove a bound that this has to work exponentially well, right? Then it could work terribly.
Okay, cool, thanks. It's basically a construction proof of these injective MPS being in the trivial phase, right? So, okay.
Yeah, thank you very much for this question. I think we should move on, and if you have time, so please let's thank Marko once more.